Okay, in this lesson, we're going to talk about how to solve some different trigonometry problems. In your textbook, it's called solving three-dimensional problems with trigonometry, although not everything's a three-dimensional problem. The idea of these questions are you're going to have to use a combination of the sine law, the cosine law, and some angle theorems to solve these questions. So let's first start by talking about bearings and what bearings are, because that's a common skill and thing we need to. Okay, so bearings are a measurement of degrees, except when we take a bearing, we don't measure from our standard position. So you think about our unit circle. I know I'm just drawing a loose circle here. Generally, this is where 0 is at, and we measure in a counterclockwise position, right? 0, 180, 270, 360, back around, right? I missed the 90, but that's generally what we call standard position, okay? Now, we're not going to be measuring from standard position with bearings. Bearings are measured, and I got it right over here, right? Bearings are measured with north taking as the reference. So instead of starting over here on our x-axis right here, we actually start right here is where we measure from. And bearings are measured moving in a clockwise direction. So we're still measuring the same degrees. It's still 360 for a full circle, but starting at north, moving clockwise. Okay, so here's a few quick examples on the handout. Bearings are always measured right clockwise from north. Pretty obvious stuff. I don't think it's too difficult to understand. 60 degrees, 240, 330, etc., etc. Okay, so generally in bearing questions, you might have two different objects, whether sometimes airplanes or boats or people. And generally what we end up having to figure out is just what's the bearing, what's the angle between those two things. So I'm going to do an example down here at the bottom. Let me just clean this. We don't need to clean the page up. Let's just keep rolling. All right, so I'm going to do a bigger problem in a moment. But the problems you're doing this week, some of them include bearings. So I want to show you that generally the work you have to do for the bearings so far is pretty simple. Okay, so in our first problem, we're going to start on the next page. I'm just taking a piece of that problem. We're going to be talking about two airplanes. Airplane 1 and airplane 2. Okay, so two airplanes. Now they have angles of depression. We're not going to worry about that right now. We'll talk about that when we get into the rest of the diagram. Let's just focus on the bearings. So airplane 2 has a bearing of 100. Airplane 1 has a bearing of 60. So I'm going to draw a little sketch here so we can make sense of the bearings first. So here's where my north is going to be, right? And obviously if you want to draw in the rest, you know, here's east, here's south, here's west. Okay, so let's just get an approximate drawing of where these are. So plane 1 has a bearing of 60 degrees. Well, from here to here would be 90 degrees, right? So it's somewhere in that first quadrant. Now, we don't have to be super accurate with this, but obviously the more accurate we can draw our picture, the better for us. All right, so here we go. Let's just draw a line, and we'll just say it's somewhere around there, okay? So I'm going to say that's where plane 1 is. And we're going to say that's about 60 degrees. Maybe it's not drawn super accurate, but you get the point. All right, so plane 1 has a bearing of 60 degrees, and I'm just going to try to draw that in right here. So from here to here is 60 degrees. All right, let's draw plane 2 now. Plane 2 has a bearing of 100 degrees, so that's just going to be a little bit past 90. Again, doesn't have to be perfect. We just want to get the general gist of where it is. So we'll just say it's somewhere over here. Here's airplane 2. Now, we don't know the exact distance. We don't know, you know, how far they are from what we're measuring from, like from here, right? But we do know the angle that they are in relation to north. Okay, so plane 2 now. Oops. Here we go. I'm just going to highlight it here. Plane 2. All right. And it has a bearing of 100 degrees. So I'm just going to draw that from here to here. Okay, so that's 100 degrees. I'll just label that right here. Okay. So from there to there, there's bearing 2 for plane 2 and bearing 1 for plane 1. Now, generally what we need in questions like this, now again, bearings questions, we could do all kinds of different stuff with this. So we're just going to take it slow here and just work on some, you know, just what we need for today. We need the bearing in between the two. So that's pretty easy because what's the bearing from here to here? That's the angle we're looking for, right? So that angle there, let's use theta for that angle. Okay, that angle there is just the difference between the two bearings. Pretty obvious, right? So the angle between the airplanes, right? I'm just calling it theta. The angle between the airplanes, right? Okay. Should use airplanes instead of planes because mathematically a plane is something very different than an airplane, but we won't get too worried about that right now. Okay, so the angle between the planes, theta, is equal to 100 degrees minus 40 degrees, or 60 degrees, right? And it's going to be 40 degrees. Okay, there we go. So that's that angle right there. So now, really, with some knowledge of how this works, you don't really need to draw a diagram to figure it out. I could have just subtracted the two bearings to find the bearing between them, right? So I could have just subtracted those two. But if it helps to draw a diagram, and sometimes you really do need to draw the diagram when there's all kinds of, more information going on. But for today, that should be enough information. So when we move on to do the question, just remember this right here, that the angle between the two airplanes was 40 degrees, because we're going to need that to solve it. All right, so let's move on to this lesson's big question. Okay, we are going to start with a very classic trigonometry problem, which is the idea of somebody up high looking down at two objects down low and determining distances between those two objects. So sometimes it's a person standing on a bridge looking down at two boats. Sometimes it's this one. This is a very common one, so we're going to start with this one, an airport tower. So you got somebody up in an airport tower, right? An airport tower that's 30 meters tall. And that person is looking down at two planes on the ground, right? And here's the information we had from that we just talked about, the idea that there's two airplanes with bearings, but they also have angles of depression. We want to find the distance between these two airplanes. So I'm going to draw it out, and for the questions I'm talking about right now, the drawing's basically exactly the same. So let's start with the airplane, or the airport tower, okay? Okay, so here's my tower up here, and right, it's 30 meters tall. Oops. Okay, so there's the top of the tower. We'll just put this as the tower here. There's the top. So this is where the person is looking out at the people down below. Here's the ground right here. And it is 30 meters high. Now, here's where things get a little bit messy. This is a three-dimensional problem. So it's hard to draw this obviously in 2 dimensions. But the idea is this person could be looking down. You'd have to kind of imagine, take your arms and point out in front of you, down at something in front of you, somewhere, in the distance in front of you. On the ground, there's 2 of them. So if he's looking down, right, he might see an airplane down here somewhere, and you might see an airplane down here somewhere. Now, this is a 3-dimensional diagram, right? So we're looking out. This could be, who knows? This could be 50 feet or something, right? Or 50 meters or 100 meters or whatever. So there's a distance here coming out, right, into the 3rd dimension. Now, I'm drawing in 2 dimensions, right? And then there's a distance between these 2 things. So I'm going to draw this a little nicer, and then we can add some numbers to it. So I'm just going to pause and draw a better version of this. Okay, so I've got my triangles drawn in, and let's locate the 2 airplanes. So the 2 airplanes, we'll put one is right here. We'll say there's where plane 1 is. Okay, and over here is plane 2, airplane 1 and airplane 2. Let me just highlight them, right? There we go. All right. And the big thing is, the question is saying we need to find the distance between these 2 airplanes. So I'm just going to label that down here. I'll just put, we'll just call that X for now. So right here, the distance between these 2 airplanes on the ground, right, is right there. Now this is supposed to be 3-dimensional. So again, this is coming out, actually it's hard to, how do I draw it coming out the screen towards you, right? But these are out in front of that tower somewhere. Okay, so there's a distance here between the tower and here, right? There's some distance here. Okay, this is basically the flat ground. This triangle on the bottom is like the flat ground. I'm trying to draw it in 3 dimensions though, right? So there's a distance coming out to where those airplanes are. Now the first big thing we can label on here, obviously we got the tower height, we know what we're solving for, is, remember those 2 bearings we just did. We said previously that the bearings between these 2 airplanes was 40 degrees, and that would be this angle right here. I'm just going to do it in a different color. I'm going to do an orange right here. So 40 degrees, that was the distance between these 2 airplanes. So like according to my diagram, north is somewhere this way, right, on the ground, but it's hard to tell. So that's why I did that diagram separately. All we really needed is what's the angle from here to here. What is that angle between those 2 airplanes? So we have that now. So on the ground, there's a 40-degree angle, and we're looking for X. Now, the last piece of information we have to get in here are the 2 angles of depression. So plane 1 has an angle of depression of 20 degrees, and airplane 2 has an angle of depression of 50 degrees. Well, if you recall the Z rule Okay, oops, hang on, I'm going to redraw this here. Okay, so I just drew a Z. Now, if you remember, the angle here is the same as the angle here. This is also called the alternate angles theorem. Okay, that's the proper name for it. We could just call it the Z rule, the Z theorem. All right, so these two angles are the same. So, for example, if this is 50 degrees here, this is going to be 50 degrees here. Okay, so this is the same thing as an angle of elevation and an angle of depression, right? The angle of depression, if I look down, let's say I'm up in the tower. This is our tower, let's say, right? And we'll just draw a line here, right? So if I look down from that tower, I'm looking down at an angle of 50 degrees. That's what it says for plane number 2 here, right? Plane 2 has an angle of depression of 50 degrees. So if someone's up in this tower and they look down, and this is where plane 2 would be, right? It would be an angle of depression of 50 degrees. Well, that means the person sitting in an airplane, if they look up at the top of the tower, would be looking up at an angle of elevation of 50 degrees. So let's take this over and look at our diagram right here. If I wanted to make a Z, right, I could really draw a line. Again, this is not perfect coming out, but see the Z here and here, right? This is that diagram right there, just trying to draw it in 3 dimensions. So that means right here, the person in the airport tower is looking down at an angle of 50 degrees at the ground, which means if someone in the plane is looking up, they're looking at an angle of elevation of 50 degrees right there. Now the same thing can be drawn on the other side. If somebody looks out at the tower, and again, we're trying to draw a Z here. This is that Z I'm trying to draw. It's just in 3 dimensions now, right? It's supposed to be kind of coming out at us. Same with on the other side, there's a Z. If somebody looks down from the tower at the airplane at an angle of depression of 20 degrees, then they're looking at this one. The airplane's looking up at an angle of elevation of 20 degrees. Okay, so now we actually have pretty much everything we need. The only thing I'm missing is these would be right angle triangles, which is kind of useful and important. All right, so I'm going to clean this up, and then we're going to start breaking this down a little more. Okay, so what we're going to try and do here is let's look at this shape that we've got drawn over here, right? Oops, I've cleaned away all the extra stuff just to keep the diagram simple. What we have here are 4 triangles. If we really focus, there's a triangle here, right angle triangle. There's a triangle here, right angle triangle. There's a triangle on the ground, a non-right angle triangle, has a 40-degree angle here. And there's also the big triangle in front. Now, this comes into play in some questions, but we don't need it for here, but we have that big face right there in the front. All right, so I'm just going to focus on the 3 triangles I put a check mark in, and I'm going to draw a little diagram of each of them, and then we're going to see what we can solve and make sense of. Okay, so I've just got a little diagram here going at the side, and what I'm going to do is I'm going to take out this triangle and just look at them in 2 dimensions, so it's a little easier to figure out what's going on. So you can see I have the tower at the top of each triangle, and I got the plane's location. So I'm talking about these right-angled triangles here. Okay, so we've got 2 right-angled triangles here. Sorry, just trying to get rid of stuff. Okay, so what do we know? Well, we know that this is 30 meters tall in both cases, because this is where the tower would be in both of these triangles. Now, what are we going to solve for? Oh, wait, before we know that, we know some angles. We know that this is a 50-degree angle here in this tower, and we know that this is a 20-degree angle in this tower. Now, if you want to solve, we could also find the third angle, because this is a 90-degree corner in each of them, right? So we could find that third angle by subtracting 90 and the other angle from 180. So 180 minus 90 minus 50. What do we get up here? Is a 40-degree angle at the top. Now that might help you solve, might not. Same with this one. How are we going to find this angle up here? Well, this is 90, this is 20, so 90 plus 20 is 110. Subtract that from 180, and we got a 70-degree angle up there. Okay, so we've got right angled triangles. Now, we can solve for 2 different things. We could solve in both triangles for the hypotenuse here, right? Our hypotenuse of our triangle. So that we could solve for. We could also find the length across the bottom. So there are 2 different things that are left to be solved for in these triangles. And you should already at this point have all the abilities to solve this. This is from grade 10. You can just use SOHCAHTOA. You can use your components, or you can even use the sine law to solve these. So I'm going to solve both of them. I'll do one using SOHCAHTOA. I'll do the other one using the sine law. It's up to you which way you want to go. But what are we going to solve for? We have to figure out, should we solve for this or this? Like I said, you could solve for both. So again, if I were your age and I was doing this on my own and I was totally, let's say, left to figure it out on my own, I would solve for both of them because I wouldn't know. I just start solving for everything, right? And that's kind of how I've learned to do different stuff, is I just kind of solve for everything I can. And eventually, it broadens my knowledge and makes me understand what pieces of information are important, which aren't. That's the difficult part of learning math, but the important part is the trial and error process, right? Because, again, I'm guiding you through how to do this, but those of you who continue to study math, that's really where it's at. It's learning by trying, seeing what works, seeing what doesn't work. But what we want to find here are the bottoms. Why would we want to find that? Well, let's look. We're dealing with this bottom triangle, right? Don't we want to solve for x here, this right here? So if I knew this length, and if I knew this length, I could probably use sine law or cosine law to solve for x. So why don't we solve for the bottom of each of these triangles, okay? So in the first one, I'll do plane 2 first, since it's over on the left side here. I'm going to start with that, and I'm going to use SOHCAHTOA. So let's see what I got. Right, let me just label what we got here. So let's label these sides. Let's call this one, we got x, so why don't we just call this one w, I guess, and this one y over here. W, y, and x, right? W, x, y. There we go. Okay, so in this case, this is going to be w. That's the length from here to here. And this is called y. You can call it whatever you want. I'm just using simple letters. Okay, so if I'm going to label this thing SOHCAHTOA style, right, if you like that, and I got no problem with that, this is your hypotenuse, right? This would be your opposite, and this would be your adjacent. Well, I'm solving for w, so what do I need, right? So, ka, and toa. All right, well, let's highlight what we're using here, right? We need to find this here. So that would be the adjacent. So we need something that uses adjacent. Well, these two use adjacent. And we don't have the hypotenuse. I need something that includes the opposite. Okay, so there you go. We're going to use tan. So let's use tan to solve this. So let me just get tan down here. Tan. Let me just clear this away so I got more room. All right, so tan. And again, the more you do this, the quicker it is. Like when I do this, I just quickly look at it. And some of you might too, right? Okay, I'm going to use tan. I'm using opposite and adjacent, right? Here we go. Or if you think of tan as slope, you're doing rise over run, 30 divided by w, right? So tan of an angle is opposite over adjacent. They're all the same thing. It's just different ways to think of it. Some people like SOHCAHTOA, some people hate it. It's just another way of memorizing, right? The same stuff. So, all right, so we're going to do tan of 50 degrees equals the opposite side, which is 30 divided by w. All right, so I'm just going to multiply both sides by w, divide both sides by tan of 50, and it just flips things around like this. And to save us time, make sure your calculator is on degrees, not radians. I know I'm kind of squishing this down here, but w, let me just move this up so I can fit more of the lesson on the page. There we go. And w is equal to approximately, I got it written down here. I'm going to write down a few decimal places, 25172. Now, you want to use as many decimal places as you can. If you want to be real accurate and be like, this is for those of you that really want to continue in math. You got to store this number in your calculator somewhere, okay? It's not good enough to just write down some decimals. Your calculator has a storage function. This is the time to learn how to use it. You can look up your calculator model number on the internet. Or obviously read the instructions that come with it. I'm kind of an instruction nerd, so I read all that stuff. But there's a storage function on your calculator, and it's invaluable to you. So take the 10 minutes to learn how to use it and really get to know how to use it well. And the next thing you know, you're going to be doing way less work. For the 10 minutes you put into really mastering how the storage and recall functions of your calculator work, you're going to find, it took me a while to put in the effort when I was your age, and then things go so much quicker because this number, I just store it in the calculator. Cool, it's stored under slot A or B or C. You have all these different storage slots, and then I just recall it from that spot. I don't have to type numbers in. It really does make things faster. All right, so anyways, that is W. So that is that length right from here to here. That's that length there. All right, so let's just leave that be. Now, let's do the other one using sine law. Some of you like sine law better because the nice thing about sine law is anything you can solve with SOHCAHTOA should be able to solve with sine law. So let's see here. We want to find y, right? So that's a length. So y over sine of the angle across from it. Well, what angle is across from it? 70. All right. Equals. Now we need a side and an angle across to match up. Well, we have 30 and 20. So 30 meters divided by sine of 20. There you go. I'm just going to multiply both sides by sine of 70, right? So what's 30 times sine of 70 degrees? Divided by sine of 20. Again, make sure your calculator is on degrees, not radians. And for y, I got it punched in here. I got approximately 82.424 ... You know, both of these keep going, and I got them stored in my calculator. Okay, so those are those two lengths. So we just found, and that's this length here. So we have just found two big pieces of the puzzle. So now we're going to focus on this bottom triangle here at the bottom, this guy, right? So I'm going to take a minute and draw another triangle, and we're going to focus on him. All right, so here we go. So this triangle I've drawn matches the bottom there. So this would be our x from here to here. I just want to match my colors up here. Here we go. X is from here to here, right? So that's this length. So I'll just leave that labeled x. Oops. All right, now what do we know so far? We know that this angle here is 40 degrees, right? So that matches this right here. So we're just looking at the triangle on the ground here. And we found the lengths of this side and this side. So let me just label them with their actual measurements. They're what we've rounded to. So W on this side was 25.172 approximately. And the other side is 82.424 approximately. Okay, so we've got a triangle, right? We don't know these angles here, no clue, but we do know to the sides. So what kind of triangle do we have? We have a side, angle, side triangle, right? We have two sides with an angle in between them. Side, angle, side. Now again, I don't memorize whether I use sine law or cosine law for this. I'm just going to move the page up a bit too. Maybe you do, or you go back and look at your notes. Obviously, you guys are learning this kind of stuff. But the idea, remember, with sine law, to use sine law, you need an angle. Okay, I have an angle. And you need the side across from it. I do not have a pair of angle, an angle and a side across from it, right? And going back over here with these ones I have an angle and a side, right? They're across from each other. But with this one I don't. So right off the bat, if you try and set up sine law, it's not going to work. So in this case, we have to use the cosine law. All right, so we're going to use cosine law. So I'm just going to write down the cosine law from the other day. C squared equals a squared plus b squared, right? So it basically starts with Pythagorean theorem, minus 2ab, and that's not a coincidence, minus 2ab cos of c. And remember, it always bookends at the front and back. Back is the angle, front is the side. Okay, so let's just substitute in everything we know, and we're going to solve for x. So x is going to be like the c in our diagram. So if I was to label this using like the letters they used here, this is like the c and this is like angle c, right? So basically, we're looking for x here, and at the very end of my formula, it's going to be cos of 40 degrees. I know that. The a and the b are like the other two sides, so it doesn't matter who's a and who's b. There you go. Okay, so let's sub them all in. So we have, we're going to have to take 25.172. I'm just going to write 25.1 for now, but again, I'm using the number in my calculator. If I don't put a couple more decimals, it's not going to be very accurate. If you're going to do it without using the storage functionality, at least use a few decimal places, all right? So this is where the storage comes in handy, because I can just recall the numbers from storage and square them. I can even save them again after I've squared them and added them. We got 82.4. I'm not kidding. Once you get good at using your storage, it's way faster. And then we're going to minus 2 times each of these, right? 25.1-ish. I just got to move this guy over here. Squished it all in too much. Sorry, it's getting a little messy. And I know it's so exciting watching me drone through these videos. 82.4 times cos of 40 degrees. All right, so how am I going to calculate this? Well, I'm going to square this number. I'm going to square this number, and then I'm going to add them. So that's kind of one section of this, right? These numbers are all multiplying here. So what I'm going to do is I'm going to do cos of 40 times it by 82.4 times it by 25.1, right? And again, I'm using more decimals than I wrote there, and times it by 2. And then we're going to subtract these two, right? So whatever we get here, right, minus, now again, be careful, because if you get a negative number here, you're going to have a double negative, but minus whatever comes from there. So just because it's going to be boring to watch me do 100 million calculations, right? You end up getting some number from that. And then the last thing is we have to get rid of the square. So we're going to take the square root of those numbers, okay? So subtract those two, see what you get. Now this is a good time for you to follow along. Let me move this down a little bit. Right? This is a time for you to maybe do some calculations. That's what we do in class, and see if you can get the same thing as me. So square the 25.1, square the 82.4, add them together. That's going to give you this number here. 2 times 25.1 times 82.2 times cos of 40. What do you get, right? If you have a double negative, be careful, right? And then the last thing is to take the square root of those. And if you do it all right, you should get approximately 65.2 meters would be the distance between the two airplanes. All right, so this is a really important question. Like in grade 11, this is a big exam question, big test question. The ones I'm going to give you to work on this week basically follow exactly this format. So I want you to just basically follow along and do exactly what I did. You can choose over here whether you like to use tan or whether you like to use the sine law. That's going to be up to you. But they all start out basically with the same information. It might be someone looking down at boats. It might be someone, but something up high looking down at two things down low. Now, we can have questions where it's the opposite. Sometimes they give us the bottom triangle, and then we got to work, to figure out what's W, what's Y, and then we use that to maybe find the height of the tower or something like that. So sometimes they give us the bottom information, and we move to the top. All right? But the main ones for you today are very similar to this question right here, okay? And you're going to have to use cosine law at the end. All right, so give them a try, and I'll move on to the next lesson.